In fact, it was about the same size as a modern-day stork. Hardly the stuff of nightmares. But appearances can be deceiving. Paleopsilopterus had something its contemporaries lacked: potential. What set it apart was its agility and speed, her traits that would become hallmarks of its descendants. While it may not have been the apex predator of its time, dwarfed by monstrous crocodilians and giant snakes, it was a harbinger of things to come. Little did the other inhabitants of ancient South America know that they were witnessing the birth of a dynasty that would reign for millions of years. As the Eocene progressed, so did the terror birds. Nature, it seemed, had plans for this lineage of avian predators, and those plans involved getting bigger, much bigger. Just 3 million years after Paleopsilopterus took its first steps, a new player entered the scene: Eluthornis, a terror bird that stood 50% taller than its ancestor, emerging as a formidable predator. But Eluthornis wasn't content with merely growing in size. It also expanded its range in a way that no other terror bird would match. While most of its kin would remain firmly rooted in the Americas, Eluthornis spread its wings and ventured across the sea to Europe. Fossil remains of this globe-trotting terror have been found in both France and Switzerland, making it the only known member of its family to have lived outside the New World. But Eluthornis was just the opening act. As the epochs rolled by, the terror birds continued to grow, adapt, and diversify. It was as if they were engaged in a relentless competition with themselves, each new species trying to outdo its predecessors in size and ferocity. The Oligocene epoch, spanning from about 34 to 23 million years ago, marked a turning point in the terror bird saga. It was during this time that the family truly began to live up to its name with the emergence of giants that would have given pause to even the bravest of prey, the Paraphysornis. This Brazilian bird was an absolute behemoth that stood 1.4 meters, or 4.5 feet tall, and tipped the scales at a whopping 180 kilograms, or 400 pounds. To put that into perspective, Paraphysornis outweighed the largest living bird today, the ostrich. This was no lightweight contender. Paraphysornis was built like a feathered tank with robust bones that spoke of raw power. Paleontologists believe that Paraphysornis hunted using a combination of kicks, slashes, and powerful jabs with its sharp beak. It's a hunting style that might remind one of a prehistoric version of mixed martial arts, with Paraphysornis as the undefeated heavyweight champion of its time. But Paraphysornis wasn't just a mindless brute. Like many of its terror bird kin, it likely possessed a level of intelligence that set it apart from other contemporary predators. Imagine the shock of a Pleistocene horse or ground sloth, accustomed to watching out for saber-tooth cats and dire wolves, suddenly confronted by this alien predator. But as impressive as Titanis was, it was dwarfed by its cousins back in South America. Kelenken, named after a mythological Tehuelche spirit, stood a towering 3 meters, or 9.8 feet tall, and weighed around 250 kilograms, or 550 pounds. This was a bird the size of a grizzly bear, with a head larger than that of a horse and a beak that could crush bone. I find myself continually fascinated by the terror birds, those avian predators that once dominated South America. Recent studies have revealed just how unique their skull structure was, especially in the larger species like Kelenken. It gave them a bite force and pecking power that was truly exceptional. I've often wondered what it would have been like to witness one of these giants taking down prey. The title of the largest terror bird is still debated, though. Brontornis gives Kelenken a run for its money. It might have been slightly shorter, but it was built like a feathered bulldozer, potentially weighing up to 400 kilograms. That would have made it the heaviest carnivorous bird of all time. Interestingly, Brontornis has been the subject of scientific controversy. Some paleontologists have even questioned whether it was truly a terror bird or even a carnivore at all. This combination of speed and size made terror birds versatile predators capable of adapting to a variety of hunting strategies. Smaller, faster species might have specialized in chasing down swift prey, like small mammals and reptiles, while the larger, more powerful species could have employed ambush tactics, or even taken on larger, more dangerous quarry. While their imposing size and fearsome beaks often steal the spotlight, the true power of terror birds lay in their highly developed senses. Recent studies of terror bird skulls and brain cases have revealed that these prehistoric predators were equipped with sensory capabilities that put them leagues ahead of many of their contemporaries. While terror birds might not have had eyesight quite as sharp as modern raptors like eagles or hawks, they were far from being visually impaired. Their eyes were well developed and positioned to provide excellent depth perception, a crucial advantage for any predator. But what really set terror bird vision apart was its versatility. These birds were equally adept at seeing in bright daylight and in the dim light of dawn and dusk, making them effective hunters around the clock. As for their hearing, the inner ear structure of terror birds suggests an acute sensitivity to low-frequency sounds. This ability would have allowed them to detect the footsteps and movements of potential prey, even when hidden by dense vegetation. The conventional wisdom held that the influx of new predators from North America, including cats, dogs, and bears, outcompeted the terror birds, leading to their eventual extinction. It was a neat and tidy explanation that seemed to make perfect sense. However, as is often the case in science, the truth has turned out to be more complex and nuanced. Recent studies have cast doubt on this simple competition-based extinction model, revealing a more intricate tapestry of factors that led to their demise. I find myself often returning to the story of the terror birds. Imagine these feathered giants, apex predators in South America, vanishing long before the arrival of placental predators in any significant numbers. It just doesn't quite fit the simple narrative of competition driving extinction. It makes you wonder what other forces were at play, something beyond a straightforward battle for survival. The success of Titanis in North America further complicates the picture. Here was a terror bird that not only expanded its range, but coexisted with large canids and felines for millions of years. Clearly, at least some of these birds were more than capable of holding their own. So, if competition wasn't the sole cause, what else could have doomed them? I suspect climate change played a significant role. The long-term cooling trend from the Oligocene to the Pliocene, culminating in a series of ice ages, would have profoundly impacted the ecosystems where terror birds lived. While it's unlikely humans directly interacted with them, the possibility that our ancestors heard stories of these creatures passed down through generations isn't far-fetched. Other megafauna that coexisted with early humans, like woolly mammoths and giant ground sloths, left lasting impressions on human culture and mythology. The near-miss between humans and terror birds also serves as a reminder of the incredible diversity of life that has existed on our planet. It's sobering to think that if the terror birds had managed to hang on for just a few thousand years longer, our understanding of the natural world might be very different today. Now, shifting our focus to another group of dominant animals on Earth, big cats. The lion may be the king of the jungle today, but the tiger stands out as the largest, most powerful, and most skilled of them all. Yet, there was one species in particular that dwarfed even the modern tiger in size, ranking among the largest cats to ever exist, the Ngandong tiger. In the early 20th century, Dutch paleontologists excavating near the village of Ngandong on the island of Java in Indonesia made a remarkable discovery. They unearthed a collection of bones belonging to a tiger. But these weren't regular Bengal tiger bones. They were bigger than anything seen in the modern world. Further research revealed even more astonishing details about this huge tiger. A less formidable rival for the Ngandong tiger would have been the giant short-faced hyena, which stood about 90 to 100 centimeters at the shoulder and averaged 110 kilos in weight. However, a group of animals that the Ngandong would not have dared to infiltrate are the dire wolves. Although they had smaller jaws and weighed way less than the Ngandong tiger, they had a unique edge over it, and that is because they hunted in packs of more than 4 individuals. In contrast, as a solitary hunter, it would have been quite difficult for the Ngandong tiger to match that intensity when attacking prey. This factor placed it at a disadvantage in the competition for apex predator status. However, that was not the only thing the Ngandong tiger had to worry about when defending the apex predator title, because around this time the early humans were notably prevalent in Southeast Asia, as over 80 individual remains have been found in that region today. So it's likely that they would have crossed paths with the Ngandong tiger. It is easy to say that such encounters would have been unfavorable for the early humans, because when it comes to size, they stood very little chance against such predators. But saying that would be undermining their intelligence. Over time, early humans might have developed tools and strategies to fight back against the Ngandong tiger, forcing the tigers back to the open woodlands, and allowing early humans to establish a foothold in the region. One thing about the open woodlands of Sunderland in the Pleistocene epoch is that it had numerous scattered trees and grasslands, which provided good visibility for stalking prey and offered a diverse array of herbivores, including many large species. However, hunting larger herbivores may not have been that successful despite the Ngandong's enormous size. For instance, stegodons were massive proboscideans closely related to elephants, with some species reaching immense sizes. Even smaller species of stegodons would have dwarfed the Ngandong tiger. Stegodons danski, for instance, is estimated to have weighed around 12.7 tons. Their thick and tough skin would have protected them from bites or claws. Then, the Ngandong tiger's best chance would be a scavenging opportunity or an attack on a vulnerable stegodon, like the young, injured, or isolated. Another example is the water buffalo known as bubulus, which are renowned for their large size and formidable strength, with some species weighing over 1,000 kilograms and moving in packs. So it would have been quite hard to face a herd of water buffalo, as their massive size, strong horns, and collective defense would overpower the tiger. The Ngandong tiger's only chance against such a colossal opponent would be to exploit their limited agility and target vulnerable areas through a surprise or flank attack. However, the Ngandong tiger succeeded more with other herbivores like Rusa timorensis, Malayan tapir, giant rats, gibbons, and wild boars. Despite its many difficulties, the Ngandong tiger still earned its place as one of the most impressive predators of all time. Since it hunted alone, its smart hunting skills and ability to target weaker prey, and even sometimes scavenge, shows us how adaptable and tough the beast was. This quality made it thrive for 1,000 years until the extreme climate shifts of the Pleistocene epoch. These included periods of intense cold, with vast ice sheets locking up water, leading to lower sea levels, followed by warmer periods with melting glaciers and rising sea levels. As a result of this, Sundaland was fragmented into smaller islands, leading to the isolated populations of Ngandong tigers with limited resources and genetic diversity. From these isolated populations emerged smaller subspecies of tigers, such as the Sumatran tiger, Bali tiger, and Javan tiger. While climate change undoubtedly played a role, scientists proposed that the presence of early humans in Southeast Asia might have been among the reasons why the tigers went extinct. They likely caused increased competition for resources or potential conflicts that impacted the Ngandong tiger population. Other factors may have also contributed to their demise. But with limited fossil records, we are left with many unanswered questions. I've always been fascinated by the giants of the past, those creatures that seem almost mythical in their power and presence. And just a short time ago, geologically speaking, one such giant walked the earth, the Smilodon, the saber-toothed cat. Even the name evokes a sense of primal force. It's strange to think that when the first Smilodon remains were found in Brazil, scientists didn't recognize them as a cat at all. For a couple of years, based on some teeth, they thought they'd discovered an ancient hyena. But as more fossils emerged, foot bones, skull fragments, and those incredible canines, the truth became clear. This was no hyena. This was a completely new kind of cat, far more massive and powerfully built than any feline we know today. They named it Smilodon populator, which translates roughly to knife tooth and the destroyer. A fitting title, I think. Researchers place this knife-toothed friend in the extinct subfamily Machairodontinae, home to most of the saber-toothed cats. Though saber-toothed cats is actually a more accurate term, since these ancient felines aren't closely related to modern tigers, or really any living cats. Their closest living relatives might be members of the Felinae subfamily, which includes our domestic kitties. Within Machairodontinae, Smilodon is part of the Smilodontini, or dirk-toothed cats. Scientists have identified 3 distinct Smilodon species: S. gracilis, S. fatalis, and S. populator. S. Gracilis, the oldest, was about the size of a modern jaguar. S. fatalis was larger, matching an African lion in size but with more muscle. But S. populator was the true behemoth, with some specimens weighing in at a staggering 1,040 pounds, about the same as a medium-sized polar bear. Interestingly, there wasn't a significant size difference between males and females. This Smilodon wasn't just large, it was built like a tank. Its heel bone was incredibly strong and elongated, leading some paleontologists to believe it could jump higher than modern lions, possibly clearing heights of 15 feet. Imagine a cat the size of a bear leaping over a one-story building. And its forelimbs were about 20% thicker than you'd expect for a cat of its size, giving it incredible strength. They were armed with fully retractable claws, razor-sharp and curved like prehistoric scimitars, proportionally enormous, even for a cat of Smilodon size. We're talking about claws twice the size of a Siberian tiger. Those impossibly long canines. They've captured my imagination for generations. Saber-teeth aren't unique to Smilodon, of course. Nature has played with this dental design in various mammals. But Smilodon perfected it, taking the concept to an entirely new level. What made its fangs special wasn't just their presence, but their sheer audacious length. We're talking about canines so long, they protruded well beyond the lower jaw, a feature uncommon even among other saber-toothed cats. To put it in perspective, Smilodon's canines could grow up to 8 inches, or 20 centimeters long. That's longer than many modern kitchen knives. They were precision instruments of prehistoric destruction, shaped like deadly daggers with sharp points and smooth, narrow sides, designed to pierce deep into flesh with devastating efficiency. You'd expect a predator with teeth like that to have a powerful bite to match. But surprisingly, studies have shown that Smilodon's bite was relatively weak, only about 1,000 newtons, which is 4 times weaker than a modern lion's. So, how did it kill? That's been a subject of much debate among paleontologists. One popular theory suggests that Smilodon was the original ambush predator. I picture it hidden in dense vegetation, waiting for the perfect moment. Then, with a powerful leap, it pounces on its unsuspecting prey. Using those muscular forelimbs and grappling hook claws, it pins down its victim. With precision, it sinks its saber teeth into the prey's soft underbelly, causing massive internal damage and blood loss. But not everyone buys this gut-stabbing hypothesis. Many researchers favor a different, but equally grim, scenario. They propose that Smilodon used its powerful build to quickly overpower its prey, then delivered a precise, lethal bite to the throat. This would have caused severe blood loss and suffocation. A quick, if not particularly pleasant end for its unfortunate victims. The reasoning goes like this. In modern cat species, the more social ones tend to be more responsive to distress calls. So, if one Smilodon got stuck, it might have called for help, attracting other members of its group who then also got stuck. It's a grim thought, but it could explain why we find so many Smilodon remains in one place. Another fascinating clue pointing to Smilodon's possible social behavior is surprisingly touching, though in a prehistoric, slightly grim sense. Some Smilodon fossils show signs of severe injuries or disabilities that would have made hunting nearly impossible. Yet, these individuals survived well into adulthood. This has led some paleontologists to propose what they call pseudo-healthcare among Smilodon. The idea is that these injured, there's a heartwarming, if speculative, image that keeps coming back to me. Smilodon families looking after their own. The fossil record hints at it. One Smilon, for example, showed signs of hip dysplasia from a young age, yet survived to adulthood. How could it have hunted alone? It's a question that suggests these cats cared for each other, much like modern lions or wolves support injured members of their pride. Of course, not everyone buys the Smilon social club theory. Some researchers point out that Smilon remains found outside predator traps tend to be more isolated, suggesting a more solitary lifestyle. Regardless, one thing is certain. The Smilon was at the top of the food chain. But that doesn't mean it didn't have competition. The Ice Age was a time of giants, and the Smilon wasn't the only predator with an appetite for mammoth-sized meals. Two of its biggest rivals were the American lion and the dire wolf. Now, if you're picturing the dire wolves from Game of Thrones, it's worth noting that while real dire wolves were impressive, they weren't quite as monstrous as their fictional counterparts. But they were formidable predators in their own right, with isotope analysis showing that they had a diet very similar to Smilion's. In other words, these predators were often competing for the same prey. So, how did the Smilon stack up against its competitors? Well, when it came to the American lion, it was probably a bit of a standoff. The American lion had size on its side, being one of the largest cats to ever exist. But the Smilon had those impressive canines, which likely served as a pretty effective deterrent. Most likely, these two apex predators tried to avoid each other when possible. But when conflicts did occur, it could have gone either way. The dire wolf, on the other hand, seems to have often come out second best in confrontations with Smilon. Evidence suggests that dire wolves would frequently abandon their kills when a Smilon showed up. It's not hard to imagine why, given those sabers being on full display. Most predators would probably decide that discretion was the better part of valor. The more widely accepted idea is that the Quaternary extinction event was the main cause. This was a period of major climate change that led to the disappearance of many large animal species in North and South America. As the megafauna that Smilodon depended on for food started to vanish, the saber-toothed predator found itself in a precarious position. It's a cruel irony, really. The very adaptations that made Smilodon such a successful hunter of large prey became a liability. It was too good at hunting giants, and when the world changed, it couldn't adapt. The extinction of Smilodon marked the end of a species and the end of an era. It was the last of the saber-toothed cats, not just in the Americas, but worldwide. Its passing brought to an end a lineage that had dominated the planet for over 20 million years. Its legacy still resonates in museum exhibits, in our imaginations, and as a reminder of the fragile balance between species and their environments. And as we face our own period of rapid change, the lesson of Smilodon is clear. Survival requires adaptation. Most apex predators face a fundamental limitation. They're trapped in one environment. Lions rule the savanna, but they're helpless in water. Great whites dominate the ocean, but can't set a fin on land. Even T-Rex, for all its might, was confined to dry ground, forced to watch as prey slipped into rivers and lakes beyond its reach. For over a century, paleontologists assumed the greatest hunters were strictly terrestrial. Then, one discovery shattered that belief overnight. Its name was Spinosaurus aegyptiacus. Longer than a bus, armed with the skull of a crocodile and the body of a streamlined aquatic hunter, this was no ordinary killer. This was the nightmare that redefined what it meant to be an apex predator, a monster that could rival and, in many ways surpass, even T-Rex itself. The first thing that strikes you about Spinosaurus isn't its length. Though at 50 to 59 feet, it dwarfs even the largest T-Rex specimens. It's not even the massive sail rising from its back like some prehistoric fin. No, what truly unsettles you is how perfectly wrong everything about this creature appears. Yet, how devastatingly effective each bizarre feature proved to be. Start with that skull, a narrow, elongated nightmare stretching nearly 6 feet long. If you've ever stared into the eyes of a large crocodile, you understand the primal fear that comes from seeing a predator perfectly designed for aquatic ambush. Now imagine that same sinister profile scaled up to dwarf any modern crocodilian, mounted on a body that could rear up 20 feet into the air. The skull alone weighed as much as a small car, yet it cut through water with the efficiency of a torpedo. They propelled Spinosaurus through water with surprising speed and maneuverability, allowing it to pursue prey through underwater mazes, where other predators would become trapped. Unlike purely aquatic or terrestrial predators, this nightmare could adapt its hunting strategy in real time. Miss your target underwater? Rise to the surface and snatch prey from above. Prey takes refuge in shallow water. Use those webbed feet for wading attacks that no other large theropod could attempt. And the hunting scenarios become even more terrifying when you consider Spinosaurus's intelligence. Crocodiles are clever, but they're still reptiles operating on instinct. Spinosaurus possessed the problem-solving capabilities of a large theropod, the same cognitive tools that made others effective pack hunters. Except this intelligence was applied to an environment where most prey had never faced anything remotely similar. Even more disturbing was how Spinosaurus turned the very act of drinking water into a death trap. For millions of years, animals had taken a calculated risk approaching rivers and lakes. Stay alert. Drink quickly. Watch for crocodiles. Suddenly, the riverbank itself became unreliable. That submerged log might be a 50-foot predator. Those ripples might not indicate current, but the approach of something that could strike from below with the force of a freight train. The fossil evidence suggests Spinosaurus didn't just occasionally venture into water. It lived there. This wasn't a terrestrial predator that sometimes waded in for a quick meal. This was a creature so perfectly adapted to aquatic life that it spent most of its time submerged, transforming ancient waterways into hunting territories more dangerous than any terrestrial predator could create. It eliminated the distinction between land and water safety, merging them into a single inescapable killing field. And we can't forget its teeth, conical, dagger-like, built to clamp down on prey that thought the water would save them. Each one was angled backward like barbed hooks, creating a living fish trap. Easy entry, impossible exit. But the teeth were just the beginning. Recent studies suggest this predator possessed sensitive organs along its snout, much like modern crocodiles, but far more specialized. In murky river water, where visibility dropped to mere inches, Spinosaurus could detect the faint press waves of swimming fish from remarkable distances. Prey animals that relied on hiding in dark sediment-filled water were essentially sitting ducks against a hunter that tracked by feel rather than sight. Every movement in the water registered on Spinosaurus's pres sensors, like sonar pings on a submarine's display. The creature could track multiple targets simultaneously, predict their movements, and position itself for killing strikes with mechanical precision. The Kelenken Formation reveals that this aquatic terror shared its territory with a deadly mix of predators, prey, and rivals. Giants like Carcharodontosaurus patrolled the inland areas. Sarasuchus, the 40-foot supercroc, competed directly with Spinosaurus for aquatic hunting grounds. Mid-sized hunters such as Rugops cleaned up Spinosaurus's leftovers, while swift predators like Deltadromeus and Bahariosaurus used speed and specialized tactics. And somehow herbivores survived this gauntlet: Ouranosaurus, Rebacosaurus, and the colossal Paralititan. The waters themselves were far from safe, filled with monstrous prey. Every species lived in constant tension with Spinosaurus's dominance. Land predators maintained uneasy truces. Herbivores relied on elaborate survival tactics just to drink, and aquatic prey developed increasingly tough defenses. The last Spinosaurus died approximately 94 million years ago. But the questions this creature raises about predation, dominance, and the very limits of survival continue to ripple through our scientific understanding. When we think of prehistoric apex predators, our minds often drift to the iconic Tyrannosaurus rex, or the fearsome megalodon. Yet, lurking in North America's ancient past was a predator so extraordinary it could make today's largest wolves look like lapdogs. Today's grey wolf may hold the crown as the largest living canid, reaching weights around 143 pounds. But rewind to the Miocene epoch, 20 to 5 million years ago, and a new apex predator emerges. Meet Epicyon, a colossal predator so fearsome it could rival a lioness in size, and had jaws powerful enough to outmatch a grizzly bear. In simpler terms, this was a dog that could eat a lion. Epicyon, meaning more than a dog, because calling it just a dog doesn't do it justice. The story of Picyon's discovery represents one of paleontology's most intriguing progressions, from misidentification to revelation. Over 160 years ago, in the fossil-rich sediments of Nebraska, scientists unearthed the first fragments of what would later be recognized as the largest canid species ever to walk the Earth. The initial discovery consisted of a fragmented lower jaw. While obviously from a large carnivore, it provided only hints of the creature's true nature. The jaw's wolf-like characteristics led early paleontologists to classify it as a subgenus of Canis, the genus that includes modern wolves, coyotes, and jackals. This classification seemed logical at the time, given the limited fossil evidence. However, as more complete specimens emerged from North American fossil beds throughout the following decades, a much more complex picture began to emerge. The discovery of complete skulls proved particularly revolutionary. These specimens revealed that while certain features resembled those of wolves, others were startlingly different. The skull. It told the whole story. It wasn't just any skull. It possessed specialized enlarged premolars and a cranial structure so robust it reminded me more of a lion or hyena than any dog I knew. When I first saw the reconstruction, I knew this was no ordinary creature. The key was in those distinctive features, those specialized premolars, and that remarkably robust jaw. They pointed directly to the Borophaginae subfamily, a distinct group within the larger canid family. In fact, the Borophaginae represent one of the most successful, yet strangely least known branches of the entire canid family. These Borophaginae, they were remarkably diverse, boasting 66 known species. They were defined by their powerful teeth, shortened but deep jaws, and something you don't see in many modern canids, a fifth toe. For over 15 million years, they dominated the North American landscape, evolving into an impressive array of forms. Some were no bigger than modern foxes. Others rivaled, or even exceeded, the size of today's grey wolves. And then there was Epicyon, the ultimate expression of the bone-crushing dog lineage. Its name literally translates to more than a dog, and it lived up to the title. Recent studies of modern canids have really helped paleontologists like myself better understand where Epicyon fits into the grand scheme of the canid family. The Borophaginae, it turns out, were a highly specialized branch, following a unique evolutionary path, distinct from the one that eventually led to modern wolves and dogs. Within the Epicyon genus, 3 distinct species emerged, each carving out its own ecological niche: Epicyon savus, Epicyon haydeni, and Epicyon elodontoides. While all 3 were impressive predators, they differed significantly in size and build. The smaller species, Savus and Elodontoides, while still formidable, possessed more gracile builds, allowing for greater agility and speed. Even these smaller species typically weighed twice as much as a modern German Shepherd. But it was Epicyon haydeni that truly pushed the boundaries of canid adaptation. Adults routinely reached lengths of 2.4 meters, nearly 8 feet, rivaling the length of a grizzly bear. They stood 90 centimeters, or 35 inches at the shoulder, about the height of a wild deer. These giants averaged between 125 and 170 kilograms, or 275 to 375 pounds, making them heavier than modern leopards and comparable to large jaguars. Some specimens would have matched medium-sized male lions in weight, making them the heaviest known canids ever to walk the earth. But size wasn't everything. Epicyon's bite was its most remarkable feature. Biomechanical studies have revealed that this ancient canid possessed one of the most powerful biting mechanisms ever seen in a mammalian carnivore. For smaller prey, they likely hunted alone or in pairs, using their impressive speed and power to quickly overwhelm victims. However, evidence increasingly points to the possibility that they also engaged in pack hunting, particularly when targeting larger prey. This idea of social hunting behavior is supported by multiple lines of evidence. Nearly all well-studied modern canids exhibit some degree of social behavior, and the fossil record too provides further support for this theory. Epicean fossils are... There's a creature from the late Cretaceous period that has always intrigued me. In a world dominated by colossal predators like Tyrannosaurus rex, where Triceratops and Hadrosaurs often bore the scars of savage attacks, this creature's fossils remain curiously unmarked. It wasn't the tallest, fastest, or most fearsome predator, but with a body armored like a tank and a tail capable of shattering bones, it defied the rules of survival, made even the mighty T-Rex think twice. This was Ankylosaurus, nature's ultimate fortress. But before Ankylosaurus, there was Epicean haydeni, a fascinating carnivore from North America's past. Its remains are among the most abundant found in the continent's deposits. This abundance suggests stable populations, a trait more common in pack-hunting species. The physical build of Epicean offers more clues to its hunting behavior. Compared to most canids, both modern and extinct, it had a more robust skeletal structure with heavier bones. While this might have limited agility and endurance compared to modern wolves, it would have been advantageous in close-quarters combat with large prey. Studies suggest they were built for powerful, explosive movements rather than long-distance pursuit, indicating they likely relied on ambush tactics or short, high-speed chases. Pack hunting would have been particularly advantageous, allowing groups to surround and overwhelm prey that might have otherwise escaped a solitary hunter. One of Epicean's most remarkable adaptations was its ability to process and digest bone, setting it apart from most other large carnivores. Its specialized premolars and thickened molars, with their short, pyramid-like shape and wide bases, closely resembled those of modern hyenas. This is a fascinating example of unrelated species developing similar adaptations to exploit the same ecological niche. Fossilized feces associated with Epicean have revealed high concentrations of processed bone material, confirming this bone-crushing behavior. This adaptation would have provided several advantages. It allowed them to extract maximum nutrition from their kills by accessing bone marrow, and reduced competition with other predators by utilizing parts of carcasses that others couldn't process. The ability to process bone would have been particularly valuable during periods of scarcity. It was clear this wasn't just another dinosaur. It demanded its own taxonomic family. The name itself is telling. Ankylosaurus, meaning fuse lizard, a reference to its remarkably fortified skeleton, and magnaventris, translating to great belly, highlighting its distinctively broad midsection. The discovery, back in 1906, was a milestone. Barnum Brown, the renowned paleontologist from the American Museum of Natural History, led an expedition through Montana's Hell Creek Formation. He unearthed an assortment of fossils that initially perplexed him. These weren't the slender bones of theropods or the broad frills of ceratopsians. He'd found fragments of bony plates, uniquely shaped teeth, and vertebrae that hinted at a heavily armored animal. Early interpretations were cautious. Brown initially speculated that the bones might belong to a previously unknown type of armored dinosaur. Further excavations in Canada and the western United States revealed more specimens, each shedding light on the creature's physical characteristics. Piecing together its skeletal framework was like assembling a prehistoric jigsaw puzzle, each discovery adding a layer of complexity. What made Ankylosaurus magniventris stand out was not only its robust anatomy, but also its ecological implications. Fossils were found in association with plant remains, indicating the lush environments it inhabited. The Ankylosaurus's skeleton was built unlike any other dinosaurs, with dense, compressed bones forming a sturdy foundation for what would become one of nature's most sophisticated armor systems. Recent studies of its bone structure have revealed that the bones themselves were uniquely reinforced with internal struts and buttresses, similar to the architectural principles used in modern building construction. This internal reinforcement provided an additional layer of protection beyond just the external armor, making every part of the animal resistant to crushing forces. The Ankylosaurus's skull alone is a marvel of design and intricate functionality. Shaped like a broad triangle, it was designed to withstand immense press. Its jaw mechanics, though less powerful than those of a carnivore, were finely tuned for grinding tough plant material. The teeth, small but ridged, created an effective tool for processing vegetation, and wear patterns suggest a highly specialized feeding strategy. What's more, the placement of its nostrils and the complexity of its nasal passages indicate not only a heightened sense of smell, but also the possibility of thermoregulatory adaptations. Speaking of armor, the Ankylosaurus's defensive system was far more sophisticated than initially understood. While we've known about its bony plates, or osteoderms, for decades, recent microscopic analysis has revealed an intricate network of blood vessels running through these structures. This suggests that the armor might have served multiple purposes, not just protection, but possibly also helping to regulate body temperature, similar to how some modern reptiles use their scales for thermoregulation. The number of these osteoderms remains a subject of debate among paleontologists, with estimates ranging from 30 to well over 100. But what's particularly intriguing is their unique construction. Unlike other armored dinosaurs that had solid thick plates, the Ankylosaurus possessed something more sophisticated: osteoderms with hollow undersides. This seemingly counterintuitive design actually represented a remarkable feat of natural engineering. The hollow structure created a dome-like formation that distributed impact forces more effectively than solid plates would have, similar to how modern motorcycle helmets use their curved design to protect riders. This adaptation made the armor particularly effective. The Ankylosaurus. Even the name sounds like armor. And that armor was truly something to behold, especially when facing a predator like T-Rex. Its hunting strategy relied heavily on delivering those powerful, bone-crushing bites. Imagine the force required to defend against that. I've always been fascinated by the engineering that went into this dinosaur's defenses. Beneath those armored plates was a network of collagen fibers that puts modern protective materials to shame. These fibers were significantly thicker than those found in modern armored animals like crocodiles and armadillos. It created a natural composite material, not unlike modern fiber-reinforced plastics. Biomechanical studies have shown that this combination of hard plates and flexible fibers could absorb and dissipate energy from impacts in ways that purely rigid armor simply couldn't match. When subjected to simulated impact tests, reconstructions of Ankylosaurus armor proved capable of withstanding forces that would have seriously injured or even killed most other dinosaurs. But perhaps the most fascinating aspect of the Ankylosaurus's defensive arsenal was its legendary tail club. It wasn't just a simple bony growth, it was a precisely engineered weapon system. It represented one of nature's most effective deterrents against predation. Recent CT scanning of tail club fossils has revealed an intricate internal structure that optimized the club for both strength and swing speed. The club itself was composed of two large osteoderms at its core, complemented by smaller ones at the tip and along the midline, all supported by a framework of highly modified vertebrae. These vertebrae were specifically adapted to handle the stresses of high-speed impacts. The mements are staggering. Specimens show the club could reach 57 cm or 22.5 inches in width and weighed approximately 23 kilos or 50 pounds. But these numbers only tell part of the story. The real marvel was in the biomechanics. Advanced computer modeling has shown that large individuals could generate impact forces exceeding 20,000 newtons, and even more remarkably, could achieve swing impulses of up to 4,800 newtons per second. To put this in perspective, a professional baseball player generates about 13 newtons per second in their swing. The Ankylosaurus's tail strike was 370 times more powerful. Recent studies using finite element analysis have even suggested that the impact force could have been focused on an area as small as a few square centimeters, multiplying its bone-crushing potential. The behavior and lifestyle of Ankylosaurus were as unique as its anatomy. While much of its life remains a mystery, fossil evidence offers glimpses into its daily routines and survival strategies. Juvenile Ankylosaurus specimens, for example, lacked the fully developed armor and tail clubs seen in adults. This vulnerability likely necessitated group behavior during the early stages of life. Trackway fossils suggest juveniles may have formed protective herds, with larger individuals shielding the more vulnerable young in the center. It's a defensive strategy reminiscent of modern muskoxen. As they matured, Ankylosaurus individuals underwent significant lifestyle changes. Adults appear to have been predominantly solitary, a conclusion supported by the rarity of adult specimens found in groups. Their solitary behavior was likely a reflection of their formidable defenses, which allowed them to traverse their environments without fear of predation. Solitary adults might have roamed large territories, primarily in search of food and suitable habitat, avoiding direct competition with other herbivores. Some paleontologists have speculated that Ankylosaurus might have used its tail club for intraspecific communication or dominance disputes. This theory is supported by observations of similar behaviors in modern animals with physical weaponry, such as bighorn sheep or rhinoceroses. The display of their tail clubs, combined with body size and posturing, could have deterred rivals without escalating into physical conflict. However, the evidence remains inconclusive, and further fossil discoveries may provide clarity on this aspect of their behavior. Ankylosaurus thrived in the rich and dynamic ecosystems of late Cretaceous North America, particularly in regions that would later become known as the Hell Creek Formation. This area was a mosaic of environments ranging from subtropical forests to open floodplains teeming with diverse flora and fauna. Fossilized plant remains suggest Ankylosaurus inhabited regions with abundant low-growing vegetation, which suited its low-slung, ground-grazing body. The climate of the late Cretaceous was warmer and more humid than today, which supported lush forests dominated by conifers, cycads, and ferns. Ankylosaurus likely played a role in shaping this ecosystem, though not as extensively as herding dinosaurs like hadrosaurs. Instead, its selective feeding habits might have influenced plant growth patterns in localized areas. The association of Ankylosaurus fossils with specific types of vegetation has led researchers to hypothesize that they may have helped disperse seeds, inadvertently promoting plant diversity. Seasonal changes would have impacted the behavior of Ankylosaurus. Fossil evidence indicates that some regions experienced dry and wet seasons, influencing the availability of food resources. Ankylosaurus may have adapted by modifying its diet or undertaking small-scale migrations to follow vegetation growth. The robust construction of its body, coupled with its ability to consume tough plant material, would have allowed it to survive in less than ideal conditions. The coexistence of Ankylosaurus with large herbivores like Triceratops and Edmontosaurus, as well as apex predators like Tyrannosaurus rex, paints a vivid picture of its ecological niche. While Ankylosaurus was not the most numerous dinosaur in its ecosystem, its defensive adaptations end its survival alongside fierce competition. Its presence in these environments exemplifies. I've always been fascinated by the idea of a creature so perfectly adapted to its world that it becomes a walking fortress. That's how I see the Ankylosaurus. Imagine an herbivore, not just surviving, but thriving in a world filled with colossal predators, all thanks to its specialized defenses and finely tuned senses. It's a testament to the power of evolution, a real-world example of natural design at its most impressive. The Ankylosaurus existed within a finely balanced food web, each species playing a specialized role. Its diet was primarily herbivorous, and its body was built to process tough, fibrous vegetation. I picture it lumbering through the landscape, its broad, low-slung muzzle stripping ferns, cycads, and horsetails. It didn't have elaborate dental batteries like some other herbivores. Instead, it relied on powerful jaw muscles to break down the plant material. Recent studies on Ankylosaurus teeth have revealed something quite surprising: a degree of dietary flexibility. While vegetation was its main source of sustenance, it seems it might have occasionally supplemented its diet with protein-rich fungi or small invertebrates, inadvertently scooped up while feeding. It reminds me of modern tortoises and iguanas, which sometimes add protein to their diets. The Ankylosaurus's digestive system was likely a marvel in itself. A large, complex gut capable of fermenting plant material. This would have been essential for extracting enough nutrients from its fibrous diet. Fossilized coprolites from similar species suggest the presence of symbiotic gut bacteria, playing a crucial role in breaking down cellulose. This process would have produced energy-rich byproducts, allowing the Ankylosaurus to maintain its massive body size. I find it particularly interesting that the Ankylosaurus's broad midsection may have been specially designed to house this extensive digestive system. The large gut volume would have provided ample space for fermentation and nutrient absorption, ensuring the animal could survive on a diet of relatively low-calorie plants. This adaptation, combined with its sturdy build and slow metabolism, likely made the Ankylosaurus an efficient grazer, perfectly suited to its environment. But it wasn't just about brute strength and a specialized diet. The Ankylosaurus's sensory capabilities were just as finely tuned as its defenses. Its most remarkable feature was its highly developed sense of smell, vital for locating food, avoiding predators, and perhaps even detecting mates. Fossil evidence reveals that the olfactory bulbs in its brain were unusually large for an herbivorous dinosaur, suggesting a sense of smell on par with, or even superior to, that of many modern reptiles and mammals. Advanced imaging techniques on Ankylosaurus skull fossils have revealed intricate nasal passages. These passages likely served a dual purpose, enhancing its sense of smell and aiding in thermoregulation. The convoluted structure of these nasal cavities, creating a larger surface area, may have allowed the Ankylosaurus to cool or warm incoming air, helping it adapt to the varied climates of the late Cretaceous period. Vision and hearing also likely contributed to the Ankylosaurus's survival. While its eyes were relatively small compared to its massive body, their placement on the sides of its skull would have provided a wide field of view. This would have allowed it to detect predators approaching from almost any direction. This peripheral vision, combined with its heightened sense of smell, would have made it difficult for ambush predators like Tyrannosaurus rex to catch it off guard. Though direct evidence for its auditory capabilities is sparse, the structure of its inner ear suggests that the Ankylosaurus was capable of detecting low-frequency sounds. This could have been useful for sensing the movements of large predators or communicating with others of its kind. There's one particularly intriguing hypothesis that I often think about. It suggests that the Ankylosaurus may have used its sensory abilities in conjunction with its defensive adaptations. For instance, its acute sense of smell and hearing could have allowed it to detect a predator's approach early enough to position itself defensively, presenting its armored back and tail club to the threat. These advanced sensory capabilities underscore the Ankylosaurus as a highly specialized organism, perfectly equipped to navigate its dangerous environment. The reign of the Ankylosaurus came to an end, along with that of other non-avian dinosaurs during the KT extinction event, approximately 66 million years ago. However, its legacy lives on in our understanding of natural design and defense mechanisms. The Cretaceous period was an era of titans. This epoch produced not only the largest terrestrial predator, but also the largest land animal ever known, a true monster mash of epic proportions. While dinosaurs dominated, other species also reached massive sizes, including flying reptiles and marine lizards. Around 82 million years ago in North America, the world witnessed the emergence of Dinosuchus, the largest crocodilian in Earth's history. This colossal crocodilian, whose name translates to terrible crocodile, was discovered in the 1850s when large, distinctive teeth were unearthed in North Carolina. Initially, these teeth were mistaken for those of a pliosaur, a type of marine reptile, leading to considerable confusion among paleontologists. They quickly realized, however, that this creature was massive and imposing. The sheer size and unique characteristics of the teeth did not align with known marine reptiles, prompting a deeper investigation. The journey to accurately identify this gigantic predator was significantly advanced by Dr. And finally, Deinosuchus riograndensis, discovered in Texas, which represents a lineage that grew even larger than its eastern relatives. The remains of riograndensis were more plentiful and better preserved, giving us a clearer picture of the ecological role and life habits of these giants. Paleontologists estimate that the average adult Deinosuchus measured between 26 and 33 feet long and weighed between 2.5 and 5 tons, more than twice the size of a male hippo, and some individuals grew even larger. Despite those initial inflated estimates, the reality of Deinosuchus's size remains impressive, solidifying its place as one of the largest crocodilians ever to have lived. The riograndensis species stands out for its sheer size. Studies of these remains, mostly from Texas, suggest that the largest riograndensis individuals could reach lengths of up to 12 meters, nearly 40 feet, and weigh around 8.5 tons. That would make them not only the largest crocodilians ever, but also heavier than most dinosaurs, except for the tyrant king, Tyrannosaurus rex. Paleontologist Thomas Lehman, who studied the Texas Deinosuchus fossils extensively, offered fascinating insights into their biology and growth. His research showed that the largest specimens had growth rings in their osteoderms, similar to tree rings. These rings gave valuable information about their age and growth rates. It's interesting to me that some of the largest riograndensis individuals showed evidence of rapid growth spurts during their juvenile years, followed by more gradual growth into adulthood. This suggests environmental factors like food availability and climate conditions had a significant impact on their growth and maximum size. Deinosuchus, with its brain case and overall appearance, bore a striking resemblance to modern alligators, including a body and snout that superficially mimicked these contemporary relatives, making it an imposing figure. But beyond this general resemblance, Deinosuchus was distinct, featuring a unique skull shape not seen in any living or extinct genus. The skull of Deinosuchus was exceptionally large, measuring up to 1.7 meters or 5.6 feet in length, comparable to that of an adult Spinosaurus. Despite its impressive size and robust build, studies have shown that Deinosuchus's bite force was somewhat surprisingly modest. A 2002 study reported a bite force of about 18,000 newtons, sufficient to crush bones, but relatively weak considering its size, especially when compared to the smaller saltwater crocodile, which exerts a bite force of 16,500 newtons. Examinations of Deinosuchus fossils reveal that its skull wasn't only massive, but also highly specialized. The arrangement of its teeth showcased a combination adapted to its predatory lifestyle. Conical and sharp front teeth for grasping prey, and blunt, robust rear teeth designed for crushing bones. This unique dental structure allowed Deinosuchus to tackle a diverse range of prey, from large dinosaurs to hard-shelled turtles, highlighting its versatility as a formidable predator. The bite force of Deinosuchus has been a topic of considerable debate and study, reflecting one of the widest ranges in estimates for any prehistoric predator. Initial research suggested a bite force of around 18,000 newtons, based on the size and structure of its skull. However, this estimate was challenged by a later study, which proposed that Deinosuchus possessed an astonishingly powerful bite force exceeding 100,000 newtons, nearly double that of Tyrannosaurus rex. This dramatic discrepancy highlights the ongoing debate within the paleontological community. Dr. Greg Erickson, who led one of the key studies on this topic, used advanced biomechanical modeling to simulate Deinosuchus's bite mechanics. Erickson's team found that the robust construction of Deinosuchus's skull and teeth supported the possibility of such a formidable bite force. With 22 exceptionally robust teeth designed to withstand high forces, and some specifically adapted for crushing large bones, this ancient crocodilian was well equipped to exert tremendous press. The latest evidence leans towards the higher end of the estimated range, reinforcing the idea that Deinosuchus could have possessed one of the most powerful bites of any known predator. Adding to their fearsome nature, Deinosuchus individuals were equipped with large, thick osteoderms, bony plates, that provided substantial protection against predators and environmental hazards. These osteoderms not only served as armor, but also supported the animal's massive body, increasing its load-bearing capacity and enabling efficient movement on land despite its size. Deinosuchus was a highly successful predator, as evidenced by its extensive range, with remains found throughout the United States and northern Mexico. During its prime, the American continent was divided by the Western Interior Seaway, a shallow sea, and Deinosuchus thrived on both sides of this seaway. It inhabited diverse environments, including estuaries, freshwater lakes, rivers, and possibly even deeper marine waters, although some believe that the marine remains could have been displaced post-mortem. The adaptability of Deinosuchus is showcased by its preference for estuaries, coastal bodies of brackish water with river or stream inlets. However, it also thrived in freshwater lakes and rivers, and was potentially present in marine environments. Its strong limbs and tail allowed it to navigate both aquatic and terrestrial settings, tolerating varying salinity levels, which further demonstrates its ecological flexibility. If Deinosuchus indeed ventured into deeper waters, it might have encountered other giant predators like Tylosaurus, one of the largest mosasaurs. This interaction could suggest a complex predator-prey dynamic within its ecosystem, influencing the behavior and distribution of various species. Deinosuchus lived alongside a vast array of dinosaurs and other prehistoric creatures. It coexisted with herbivorous dinosaurs like Anodontosaurus, Gryosaurus, Cosmoceratops, Eutrixeratops, and many others. Bite marks on the bones of hadrosaurs and other dinosaurs provide clear evidence of its predatory behavior. Deinosuchus's presence likely impacted the distribution and behavior of these animals, asserting itself as an apex predator in its habitat. Despite its dominance, Deinosuchus vanished from the fossil record around 73 million years ago. The reasons for its extinction remain unclear. Though climate changes, sea level fluctuations, and competition with emerging predators are potential factors, its extinction marked the end of an era. but the fossil remains of Deinosuchus continue to provide valuable insights into the life and ecosystems of the late Cretaceous period. In the world of big cats, the tiger, lion, and jaguar have always fought for supremacy, each vying to be the ultimate apex predator. But there's one ancient beast that towers above them all: the American lion. This was no ordinary feline. It was the largest to ever walk the earth. Imagine a creature so massive that some individuals weighed as much as an adult brown bear, easily dwarfing today's biggest lions. This isn't just another big cat. It's a legendary predator that dominated its world like no other, leaving modern felines in the dust. The story of this magnificent creature's discovery begins in the humid lands of Mississippi during the early 1800s. When paleontologists first unearthed fragments of its skull, they initially believed they had found remains of an unusually large domestic cat, placing it in the genus Felis. This classification, however, would prove to be just the first chapter in a much longer story of scientific discovery and reclassification. As more specimens emerged from the Earth, scientists quickly realized they were dealing with something far more impressive: the sheer size and distinctive features. The American lion. The name conjures up images of a creature both familiar and alien. I find myself captivated by the fact that for a time North America was home to a feline that dwarfed even the largest modern big cats. Recent research has revealed that this massive predator wasn't quite what we first thought. It wasn't just a subspecies of the modern lion, but its own distinct species. Modern science has a way of reshaping our understanding of prehistoric life. It's fascinating how detailed anatomical studies revealed crucial differences that set the American lion apart. A more robust build, proportionally longer limbs, and the absence of a prominent mane in males. These distinctions led to its reclassification as its own species. Panthera atrox, the cruel panther. DNA analysis has shown that it emerged from an isolated population of cave lions that became trapped south of the North American ice sheets approximately 340,000 years ago. This separation occurred during a crucial period of the Pleistocene epoch, leading to rapid adaptations to North American environments. While modern lions are indeed their closest living relatives, the last common ancestor between these species lived somewhere between 500,000 and 1.9 million years ago, a testament to how quickly changes can occur under the right conditions. The sheer size of the American lion sets it apart from any feline, living or extinct. On average, these beasts were about 25% larger than today's African lions. Male American lions typically weighed between 351 kg, 774 lb, and 420 kg, 930 lb, already making them substantially larger than any living big cat. However, the most impressive specimens, discovered in 2012, have been estimated to weigh an astounding 523 kg, 153 lb, equivalent to the weight of 8 adult humans combined. To put this in perspective, even the largest recorded Siberian tigers, which are the biggest living cats today, rarely exceed 300 kilos, 660 lb. The American lion's only real competitor for size was the equally impressive Smilodon populator, which could reach weights of up to 470 kilos, 140 lb. However, the discovery of those exceptionally large American lion specimens in 2012 firmly established Panthera atrox as the heavyweight champion of the feline world. What makes the American lion particularly remarkable is that, despite its enormous size, it maintained the agility and speed characteristic of big cats. Conservative estimates suggest it could reach speeds of over 30 meters/picus, 48 km/h, faster than any human athlete and comparable to a charging warthog. This combination of size and speed would have made it an extraordinarily effective predator. The hunting strategy of the American lion likely relied heavily on ambush tactics, a conclusion drawn from both its anatomical features and the hunting behaviors of its modern relatives. Its robust bone structure and powerful muscles would have allowed it to quickly overwhelm large prey, while its long legs provided the burst speed necessary for successful ambush attacks. Fossil evidence provides compelling insights into its hunting capabilities. The discovery of Blue Babe, a remarkably preserved steppe bison in Alaska, bears the unmistakable marks of an American lion attack, including deep claw wounds and distinctive bite patterns that match the predator's dentition. Even more telling are the fossils found at sites like Natural Trap Cave in Wyoming, where researchers have uncovered numerous prey species bearing the characteristic damage patterns of American lion predation. What truly set American lions apart from their contemporary rivals wasn't just their size, but their exceptional adaptability and territorial dominance. Recent studies of fossil deposits across North America have revealed fascinating insights into their social structure and hunting territories. Unlike modern African lions that typically control territories of 100 to 200 kilometers, evidence suggests that American lions commanded vastly larger ranges, some extending up to 500 kilometers per pride. This massive territory was a necessity, not a luxury, given their enormous size and corresponding caloric needs. The fossil record tells us an intriguing story of their social dynamics. While modern lions live in prides of up to 15 individuals, American lion social groups appear to have been smaller but more efficient. Bone assemblages at key sites like the Page-Ladson site in Florida and the Rancho La Brea deposits suggest groups of 4 to 6 adults working together with devastating effectiveness. Their smaller pride size, combined with their larger individual mass, meant each pride needed to bring down fewer but larger prey animals to sustain themselves. Perhaps most fascinating is the evidence of their den sites discovered in caves across the American West. These sites, particularly those found at the Grand Canyon region, show signs of multi-generational use, with some caves bearing marks of occupation spanning thousands of years. So mesmerized by its size, he named it after an Aztec serpent god and an aircraft manufacturing company, Quetzalcoatlus northropi. It's become common knowledge that Quetzalcoatlus is the biggest pterosaur, the largest flying animal in history. Yet, despite its size and cohabitation with the Tyrannosaurus rex, little is known about its biology. Its wingspan was initially estimated at over 21 meters, wider than an F-22 fighter plane, though those numbers were a bit exaggerated. Paleontologists now believe it was closer to 10 to 12 meters wide, still larger than an F-16. It stood roughly the same height as a giraffe. Some researchers believe it may have weighed around 250 kilograms, close to the weight of a grizzly bear. While Quetzalcoatlus lawsoni was smaller, it still had a wide wingspan, perhaps 4.5 to 6 meters. For years, the largest Quetzalcoatlus was considered the largest pterosaur ever, but recent discoveries have challenged it in size and weight. There's Hatzegopteryx, for example, from Europe, with a similar wingspan but greater weight and a larger skull. Still, Quetzalcoatlus remains the largest pterosaur to have flown over North America. Quetzalcoatlus. Even the name sounds like something out of a dream. But this creature, this flying reptile, was very real. I've always been captivated by the idea that something so immense could have soared through the skies. It had an extraordinary metabolism to support its way of life, with a physiology similar to other pterosaurs. For a long time, scientists assumed it was cold-blooded, like most reptiles. But now, we're quite that Quetzalcoatlus was warm-blooded and surprisingly active. Warm-blooded or cold, I don't think anyone would call it beautiful. And contrary to what you might expect, it's unlikely that any modern flyers are actually descendants of this animal. Its long, pointed beak resembled a modern stork's, but without the hooked tip. Excavations have revealed that the skull of Quetzalcoatlus northropi was larger than that of Quetzalcoatlus lawsoni, suggesting that northropi was the larger of the two species. What's fascinating is that Quetzalcoatlus could rotate its head 180 degrees, giving it a huge advantage in locating prey and avoiding ambushes. This ability led some to believe that it might have actually lived and hunted primarily on the ground. The idea was that it was simply too heavy to fly and was better suited to a terrestrial life. This flightless theory, which emerged around 2010, never really took off, so to speak. Almost all paleontologists now agree that it was indeed capable of flight, thanks to a recent discovery. The unearthed bones suggest that Quetzalcoatlus had incredibly light, almost potato chip-like bones, which would have made flight easier than we previously thought. This revelation, though, brought up another major question. How did Quetzalcoatlus even take off? And how exactly did it fly? Many theories have been proposed, picturing this enormous reptile leaping into the air by flapping its wings, or perhaps lurching forward on its wingtips, almost like a vampire bat. It might have even crouched low before launching itself 8 feet into the air, giving it enough room to spread its wings and finally take off. Its secret weapon, those strong hind legs providing the massive push needed to jump. One study suggested that Quetzalcoatlus was a remarkable flyer, engaging in brief bursts of powered flight before gliding. It could reach a top speed of 130 kilometers per hour, or 80 miles per hour, and sustain that for perhaps 7 to 10 days, giving it an extraordinary range. Despite the relatively small size of its torso compared to its bulk, it was extremely dense and packed with massive muscles. These giants could likely take off with a single leap and maintain altitude with just a few flaps of their wings. After that initial launch, they could probably fly non-stop for 16,000 kilometers, only flapping occasionally to maintain altitude and guide their course. Its short wings were made of tightly packed muscle fibers that end flexibility and strength, allowing for precise adjustments in the air. The extraordinary flight techniques of Quetzalcoatlus even inspired a Johnson Wax-sponsored mission, to construct a model flying machine to test flight simulations. While this skimmer feeding idea gained popularity, it wasn't scientifically tested until 2007. A study revealed that for such massive flying creatures, the energy requirement for skimming would be too great due to considerable drag, making it impossible. A year later, another study of Ashdashid dietary habits suggested that the remains of the reptile family aren't found close enough to large bodies of water to support skimming. The scientists found evidence that the anatomy of Quetzalcoatlus is completely different from any known skimmer. A skimmer's neck is designed to absorb sudden impacts, but fossils have shown that Ashdashids lacked these adaptations. In reality, they would likely break their necks simply from the strain of attempting to push their lower jaws through the water. On the contrary, their anatomy is similar to modern storks, indicating that they most likely pursued and hunted small animals on land. For a while, Quetzalcoatlus and its relatives were envisioned as giant vultures, scavenging the carcasses of dinosaurs and other dead animals. But with time and ongoing scientific advancements, we are starting to learn more about the habitat of this unique creature that once ruled the skies of the late Cretaceous Maastrichtian age of North America. Quetzalcoatlus most likely lived in a variety of settings during the late Cretaceous period, including coastal regions and inland plains. These enormous landscapes. The thought of encountering Quetzalcoatlus. It makes me grateful to live in a time beyond their reign. Imagine walking through a forest and seeing a creature with a wingspan the size of a small plane. It's almost unbelievable, isn't it? Scientists believe that Quetzalcoatlus lawsoni may have lived in swarms around alkaline lakes, behaving as sociable waders. But Quetzalcoatlus northropi, it seems, was likely a solitary hunter, roaming freely inland. And it wasn't the only giant of its time. Fossils suggest that creatures resembling Tyrannosaurus and Torosaurus might have coexisted with Quetzalcoatlus, although we need more research to be certain. Alongside the iconic Alamosaurus, Quetzalcoatlus might have crossed paths with other herbivorous giants and formidable predators, like the mighty T-Rex, Dromaeosaurus, Triceratops, Albertosaurus, Edmontosaurus, and Dakotaraptor. In the skies, Quetzalcoatlus likely shared its domain with other pterosaurs, like Pteranodon and Nyctosaurus, coexisting within those extinct ecosystems.